Hey everyone, today we're going to work on identifying redox reactions. So, for oxidation reduction reactions, also known as redox reactions, these are defined as a reaction in which electrons are transferred from one reactant to another. And actually, one of the most familiar redox reaction is the corrosion of a metal. So, corrosion is just the conversion of a metal into a metal compound. For example, the green coating that you see forming on copper roofs, or whenever you see iron is rusting. So this is actually a big slide that I would have you guys write down to understand kind of the difference. We talked about oxidation and reduction a little bit when we went over net ionic equations. So that's why it may sound familiar, but we're going to go back over it just in case you forgot anything. Oxidation is called the loss of electrons by a substance, and typically this means that the substance's oxidation number is increasing. Reduction, on the other hand, is where you're gaining electrons, and so your oxidation number is actually being decreased or reduced. So notice kind of how the number of electrons and oxidation number kind of are going to be opposites of one another. So one goes up, the other goes down. One thing to note about oxidation reduction reactions is if one reactant is losing electrons, in other words, being oxidized, the other one has to be gaining them or is being reduced. The oxidation of one substance has to be accompanied by the reduction of some other substance. Hence why we often just abbreviate their name as redox. Now, there is something that I mentioned last semester that my college professor taught me, and that is Leo goes gur. I did mention it. It means losing electrons oxidized, gaining electrons reduced. So if that kind of helps you, that works as well. So here it says in every redox reaction, the oxidation number of at least two elements have to change. One of the oxidation numbers must increase and the other must decrease. If all of the elements' oxidation states actually remain the same, there is no redox reaction occurring. Here we have an example of chlorine mixing with potassium iodide to yield iodine and potassium chloride. Note here that the reason we learned oxidation is we're going to apply oxidative states to these to see if a redox reaction happened. Here we have chlorine. It's a single element by itself, so it gets an oxidation number of 0. So that's why 0 is listed here. If we look at potassium and iodide, know that potassium is a group 1A metal, so it's a +1. Iodide is a -1 because it's a halogen. So notice here, those are the oxidation numbers that were assigned. I2 is a single element by itself, so it receives the oxidation number of 0. And then potassium chloride, potassium is a group 1 metal, which is always +1. And then Cl is a halogen, so that is a -1. Now that we've kind of identified oxidative numbers, we can see how they changed. Note that chlorine went from an oxidative number of 0 to an oxidative number of -1. So I became more negative. That means I have gained a negative charge or I have gained electrons. Remember, gaining electrons is reduced. So again, reduction, gained electrons. So more negative. Over here, potassium was a +1 and it stayed a +1. So nothing is happening to potassium. So it's not being oxidized or reduced. Iodine, on the other hand, went from -1 to 0. So notice here I have become more positive. In order to become more positive, that means I need to lose a negative charge, so I'm losing electrons. That way I am more positive. Losing electrons, oxidation. So we can actually determine if a reaction is going to be a redox reaction and then determine who is being oxidized and who is being reduced. And that's exactly what we're going to do in the following problem. In order to do this, first thing that we need to understand and the first thing that we need to do is to assign redox reactions or oxidative states. So here I have a lone element of manganese. That's oxidative state of 0 automatically. Over here, lead is by itself, and so that is an oxidation number of 0 automatically. So then we need to determine oxidation number of the following two. So if we look at PbNO3 with a 2 charge, what we should automatically see is that lead is a metal, so we can uncross our charges. We can say Pb has a 2 plus charge according to our oxidation rules. And then NO3, there's nothing down here, is a -1. Since this is a lone element, that we can say Pb is a +2. Now with NO3, -1, this is a polyatomic, so we can actually solve for this one ourselves. We can say that equals -1. There are 3 oxygen. This is typically a -2. Plus, I don't know my nitrogen, so I'm going to plug in X for that. Here you get X is -6 equals -1. And then you can add 6 to the other side and see that X actually equals +5. So that +5 is illustrated for nitrogen. And oxygen, we said in our equation, was -2. One thing that's awesome about polyatomics is that if polyatomics are never going to change their oxidation numbers, so if I have nitrate here and it's a +5, over here it's going to stay a +5, and oxygen's going to stay a -2. So then we just have to figure out manganese, and manganese, if you uncross this 2 up here, we're going to realize manganese is also a +2 oxidative state. Once you assign oxidation numbers, we need to figure out who changes. So if I look over here, manganese to manganese changed. Manganese went from 0 to a +2. Notice that it became more positive, and in order to become more positive, I had to lose electrons. Losing electrons means that Mn was oxidized. Again, because it became more positive, lost electrons. Note here, if I look at Pb also changed. Pb went from +2 to 0, so it's become more negative. So in order to become more negative, I needed to gain electrons, and so that's reduction, so reduced. Note that NO, N, and oxygen did not change oxidative states, so they're not part of that. So Mn and Pb are the ones being oxidized and reduced respectively. So yes, this is an oxidation reduction reaction. Let's look at this one. It says, which of the following equations represent redox reactions? And then if it's redox, which element is being oxidized and which one's being reduced? First thing we need to do is assign oxidation numbers. So let's go ahead and do that. For sodium, there is a rule for sodium. It is a group 1 metal, so it should always equal +1 because it is a group 1 metal. In terms of hydrogen, hydrogen is going to be typically a +1 if it's bonded with a nonmetal. So note here, it's a +1 because it's bonded to my chlorine, which is a nonmetal. Over here, this is going to be a +1 because it's actually bonded with my oxygen. And then over here, this one's going to be a +1 because no, it's bonded with an oxygen. When we look at this, oxygen typically is going to be a -2 unless it's a peroxide, fluorine, or a superoxide. And here, this is not a peroxide or anything, so this is -2. Note that when we add them up, they equal 0. -2 plus 2 gives me 0 for my neutral compound. If I look at this one, -2, and then here 2 times +1, 2 minus 2 still gives me 0. Now we have the chlorine. Now halogens are typically going to be -1 unless bonded to a more electronegative atom such as oxygen or fluorine, and it is not. So notice here, +1 -1 balances out to be 0, and same thing here. Now that we have identified oxidation states, we can see has anything changed. Note here, sodium did not change. Note my oxygen did not change. My hydrogen did not change from either side, and my chlorine did not change oxidation numbers. So this is considered not a redox reaction. And this is our last example. We need to figure out, is it a redox reaction, and then which element is being oxidized and which one is being reduced if it is a redox. First thing, again, is to assign oxidation numbers. One thing to note is that this is an element by itself, so its oxidation number is 0. If we look at this one, K and K, that is a first column or first group element, so those are always a positive 1. So we need to figure what NO3 is versus NO2. Notice these are not the same polyatomic because this one has 2 oxygen and this one has 3. So we actually need to solve for these. KNO3. We're going to equal this to 0 because it's a neutral compound. We know that potassium is a 1, and then here I have 3 oxygen, and oxygen is typically a -2, plus, I don't know my nitrogen, so I'm going to put X, and then we can go ahead and we can solve. So we have, that's -6, so X minus 5, because my 1 over there joined up, equals 0, so X equals +5. So here we're going to see that oxygen is a -2, and nitrogen is a +5. When we look at this one, we have KNO2. We're going to equal this to 0. We have 1 from our potassium, X from our nitrogen, 2 oxygen, which gets a -2. When we combine these, we get -4 plus 1, so we get X -3, X equals 3. Note here, my oxygen is still a -2, but my nitrogen is a +3. From there, we need to see what changed. Note that my potassium did not change, but my nitrogen did. Note here, my nitrogen became less positive. So if I am becoming less positive, that means that I am going to be gaining electrons because I'm gaining a negative charge. So gaining electrons means you are being reduced or reduction. Note that my oxygen doesn't appear to be changing if I go look at these 2 oxygen, but note I have an oxygen over here. So in fact, oxygen did change. So here I see my oxygen is going from -2 to 0, so it's becoming more positive. In order to become more positive, you're going to have to get rid of some of that negative charge. So losing electrons, oxidized. So my N is being reduced and my oxygen is being oxidized. Okay. And that's the end of today's lesson. Let me know if you have any questions, and I hope you guys have a great day.